Hello everyone. In this lecture I am going to discuss about solution of homogeneous linear differential equations with constant coefficients. First let us discuss with the definition. Start with definition. What is linear differential equation? A differential equation is said to be linear differential equation if the dependent variable and its derivatives of the degree 1 and there is no product of dependent variable and its derivatives, then the D is known as linear D. For example, if you write this is one linear D. This is linear D of degree 1. Clearly it is of degree 1 and there is no product of dependent variable and its derivatives, and here dependent variable is y, independent variable is x, and clearly this is of degree 1 and there is no product. So this D is known as linear DE and this is of order 1. Similarly we can write even second order linear DE, third order, fourth order. Like this we can write nth order linear differential equation. Nth order linear DE looks like this. This is standard form of nth order linear differential equation. Now this is nth derivative plus some constant into n minus 1 and so on. This right hand side is a function of x. This is called the nth order linear differential equation. Here p1, p2, so on, pn are constants. And this is known as non-homogeneous linear differential equation if this q of x is not equal 0. If this is equal 0, then we say it is a homogeneous linear D. Now in this topic we are going to discuss about solution of homogeneous linear DE only. Now first to find solution of homogeneous linear DE with constant coefficients, first one should write the given DE in operator form. Now what is a differential operator? Now this D is known as differential operator. This capital D is known as differential operator. D means d by dx. D square means d square by dx square, and so on. D power n means d power n by dx power n. Now this D is known as differential operator. Using this differential operator we can write the given differential equation in operator form. For example, let us say this is the given differential equation. Let us say this is the given differential equation. If you write in operator form, it looks something like this. Now in place of d square by dx square, we can write d square y plus xy equals to x square. Now this can be rewritten as d square plus x into y equals to x square, something like this. Now the given differential equation we are writing in operator form as like this. Now this D is known as a differential equation in operator form. Now how to find now this is the general form of linear differential equation in operator form. Now let us say this is the given differential equation, nth order linear DE with constant coefficients. Now this can be written in operator form as like this. In place of d power n by dx power n, that can be written as d power n. In place of d power n minus 1 dx power n minus 1, that can be written as d power n minus 1, and so on. Now we are writing this linear DE in operator form as like this. Now here f of d looks like a polynomial in D. Now this is known as polynomial in D, and q is a function of x, are constants. Now we are trying to solve solution of linear DE with constant coefficients. In this case we are talking about solution of homogeneous linear DE only. Now to solve solution of homogeneous linear differential equation, first we need to write auxiliary equation. What is meant by auxiliary equation? Now as I discussed, as I said, given differential equation can be written in operator form as like this. This is in operator form. Now here f of d is nothing but polynomial in D. If we write an equation something like this, This equation is known as auxiliary equation. In place of D, even we can write M also. Now this is known as auxiliary equation. Now we are writing auxiliary equation like this. Now you find roots of the auxiliary equation. Let us say roots of the auxiliary equation are like this, m1, m2, so on, mn. Depending on these roots, we write the solution of homogeneous linear differential equation. For example, let us say, if the roots are all are real and distinct, if roots are real and distinct, then solution can be written as y equals to c1 into e power m1x plus c2 into e power m2x plus and so on. Here m1, m2, so on, mn are roots of this auxiliary equation. For example, here we have written like this. For example, let us say roots are 1, 2. If roots are 1, 2, then solution of that dE can be written as y equals to a constant c1 into e power 1 into x plus c2 e power second root into x. Now this gives the solution of that particular differential equation having roots as 1, 2. For example, here we have written roots of that auxiliary equation are 2, 3, 5. So solution of this differential equation having roots of auxiliary equation are 2, 3 as 5, as can be written like this: y equals to c1 e power 2x plus c2 e power 3x plus c3 e power 5x. Now this is the first case. The first case is when roots are real and distinct. Now let us see the second case, when the roots are real and repeated, let us say. Now here we have taken m1, m2, m3, so on, mn. These are all roots of the auxiliary equation. Let us say out of these auxiliary equations, let us say 3 roots are same. For example, let us say 3 roots are same. If 3 roots are same, then complementary function or solution of homogeneous linear DE can be written as y equals to c1 plus c2x plus c3x square into e power 2x. I am saying here 3 roots are repeating. So we are writing c1 plus c2x plus c3x square into e power 2x. Here 2 is repeating thrice. So we are writing complementary function as like this. Now this is called solution of homogeneous linear DE having roots of auxiliary equation as like this 2, 2, 2. Okay. If all the roots are, let us say, repeating, in that case we write a complementary function as like this, or solution as like this: y equals to c1 plus c2x plus c3x square plus and so on cn x power n minus 1 into e power m1x. Now this is the way to write solution of homogeneous linear DE if all the roots are repeated. Let us discuss the next case. If the roots are, let us say, complex. For example, let us say roots are like this. I am taking a root is alpha plus I beta. The other root is alpha minus I beta. In this case, how to write solution of that DE? The solution can be written as c1 into e power alpha plus I beta into x plus c2 into e power alpha minus I beta into x. If you simplify this one, this can be written as y equals to e power alpha x into c1 cos beta x plus c2 sin beta x. Now this is the way to write a solution of linear DE with constant coefficients when roots of the auxiliary equation are complex and distinct. Roots of the auxiliary equation are complex and distinct. Okay. This roots of the equation are complex and distinct. Then we can write like this. Now this is the way to write a complementary function, or we can say solution, when roots of the auxiliary equation are complex and distinct. Here we have taken 2 roots as like this, alpha plus I beta, alpha minus I beta. Here we have taken these two roots as complex roots, and the remaining roots are real and distinct, let us say. So corresponding to these two roots, we are writing solution as like this: c1 cos beta x plus c2 sin beta x into e power alpha x. Corresponding to these roots, we are writing solution as like this: c3 e power m3x plus and so on, cn e power mn x. Here we are writing n constants because we have taken nth order linear DE with constant coefficients. Now for example, here we have taken roots as 2 plus I3, 2 minus I3, and other two roots are real and distinct. Corresponding to these complex roots, we write a complementary function as like this. Here real part is alpha. In this case, this is called real part. This alpha is called real part. This is real part. And this beta is called imaginary one. Here we write e power alpha x into c1 cos beta x. Here beta is 3 plus c2 sin beta x. Now this is the solution corresponding to this complex roots. Now this is corresponding to distinct and real roots: c3 into e power 4x plus c4 into e power minus 4x. Now let us discuss when roots are repeating, complex roots are repeating. For example, here, let us say alpha plus or minus I beta, I am taking twice, let us say. This root is repeating twice like this. Here alpha plus or minus I beta we have taken. Here also we have taken alpha plus or minus I beta. Now corresponding to these complex repeated roots, we write a complementary function as like this: e power alpha x into, here total 4 roots are there, so we get 4 constants here: c1 plus c2x into cos beta x plus c3 plus c4x into sin beta x, and this solution is corresponding to these roots, distinct roots. So this is the way to write a solution of homogeneous linear DE when roots are complex and repeated. Here we have taken one example. Let us say roots are like this. Roots of auxiliary equation are minus 1 plus or minus 2i, minus 1 plus or minus 2i. Here complex root is repeating and other roots are distinct, real and distinct. Then complementary function or solution of linear DE is like this. Corresponding to these complex roots, we write complementary function as like this. Here alpha is minus 1, beta is 2, so e power minus alpha x into c1 plus c2x cos beta x plus c3 plus c4x sin beta x plus, now these two are corresponding to real and distinct roots. So this is the way to write a solution when roots are complex and repeated. Now this is a procedure to find solution of homogeneous linear differential equation with constant coefficients. So what is the procedure? First they will give one differential equation. Let us say, for example, I am writing d square y by dx square plus 2 dy by dx plus y equals to, for example, I am writing, let us say this is the given differential equation. To solve this one, what is the procedure? To solve this differential equation, let us consider this differential equation as like this: d square y by dx square plus 2 into dy by dx plus y equals to 0. Why I am taking right hand part as 0? Because we are considering homogeneous linear differential equations only. So for the homogeneous linear differential equation, we should consider right hand part as 0 to find solution of that differential equation. Now write down this differential equation in operator form. This can be written in operator form as like this: d square y, in place of d square by dx square can be written d square. In place of d by dx we can write d. We are writing in differential operator form plus like this. Now this can be rewritten as like this: d square plus 2d plus 1 into y equals 0. First step is write the given differential equation in operator form as like this. That is the first step. Write the differential equation in operator form as like this. After writing the differential equation in operator form, then write down auxiliary equation. Now f of m equals to 0 gives auxiliary equation. In this case, this is f of d into y equals to 0. Write down auxiliary equation as f of m equals to 0. Now this gives auxiliary equation, or write down the auxiliary equation. Solve that equation for m values. If you solve this equation, we get some roots. Depending on the degree of that equation, we get the roots. If in this case f of m is a polynomial of degree 2, so we get 2 roots. Solve that one, we get 2 roots. Now depending on that roots, if the roots are real and distinct, we write solution as in the first case, what we have discussed in the first case, like that we write. If it is in the second case, roots are real and repeated, we write as we discussed in the second case, and so on. Now this is the procedure to find a solution of homogeneous linear DE with constant coefficients. Let us discuss some examples. Solve y double dash plus 3y dash equals 0. Now this is the given differential equation. Now clearly it is a homogeneous linear DE because right hand part we have taken as 0 with constant coefficients. Clearly here coefficient of y dash is 3 and coefficient of y double dash is also 1. So this is the linear DE with constant coefficients and homogeneous. Now this we will solution of this one. Now first write down what is the given differential equation. I am writing what is given. Given d square y by dx square plus 3 into dy by dx equals to 0. This is the given differential equation. Now to solve this differential equation, first step is we should write this dE in operator form. Now this can be written in operator form as like this. One can be written in operator form as like this. Here in place of d square by dx square we write capital D square. I am writing that plus 3 times. In place of d by dx we write capital D into y equals to 0. Now where capital D is nothing but d by dx. This is called differential operator. Okay. Now let us simplify this one. This can be written as d square plus 3d into y equals to 0. Now we have expressed the given differential equation in operator form as like this. D square plus 3d into y equals 0. Now let us solve this one. Now what is the auxiliary equation? To solve this one, we write auxiliary equation. Auxiliary equation is given by f of m equals to 0. This gives the auxiliary equation. Now that is nothing but m square plus 3m equals 0. This gives auxiliary equation. Let us solve this equation. If we solve this equation, we get a 0 and minus 3 as roots. These are the roots of this auxiliary equation. Now clearly the roots are real numbers and clearly these are distinct. Roots are real and distinct. Write down here. I am writing here roots of auxiliary equation are real and distinct. If roots are real and distinct, we have a method to write solution of this differential equation. Then solution of this d is given by required solution of 1 is given by y equals to, here roots are real and distinct. One of the roots is 0, the other one is minus 3. So c1 e power 0 into x plus c2 e power second root is minus 3 into x. So solution of the given d is c1 plus c2 e power minus 3. This gives the solution of the given differential equation. Now let us discuss next problem. Find a solution of d square y by dx square plus 2 dy by dx plus y equals to 0. Let us say this is the given differential equation. Now we want to find solution of this differential equation. Again it is a linear DE because this derivative of degree 1, this derivative of degree 1, and clearly dependent variable is also of degree 1 and there is no product of dependent variable and its derivative. So it is a linear differential equation and clearly it is a linear DE with constant coefficients because here coefficient is 1, here 2, here 1. So it is a linear DE with constant coefficients and clearly it is a homogeneous because right hand part is 0. So let us discuss solution of this one. So let us write a given differential equation. I am writing what is given. Given d is d square y by dx square plus twice dy by dx plus, let us say this is given differential equation. Write this in operator form. One can be written as, one can be written as like this in operator form, d square plus 2d plus 1 into y equals to 0, where d is nothing but d by dx. In place of d by dx we are writing d, in place of d square by dx square we are writing d square. So this is in operator form. Now write down auxiliary equation. Auxiliary equation is given by, auxiliary equation is given by m square plus 2m plus 1. Let us find solution of this equation. Solution of this equation, this can be written as like this. So we get minus 1 as solution of this auxiliary equation. Now clearly your roots are real only, but roots are not distinct here repeated. So in this case solution of this DE can be written as required solution of 1 is given by y equals to, here two roots are real and repeated, so we write c1 plus c2x into e power minus x, where we should write even this sentence also, where c1 c2 are arbitrary constants. Now this gives the required solution of this differential equation. Now let us discuss next problem. Solve d square plus d plus 1 into y equals to 0. Let us say this is the given differential equation. Now directly this is given in operator form and clearly it is a homogeneous one, clearly it is a linear DE with constant coefficients. So let us discuss this. What is given, write down first. This is given d square plus d plus 1 into y equals 0. Now write down the auxiliary equation. Auxiliary equation is given by m square plus m plus 1 equals 0. This gives the auxiliary equation. Now let us find the roots of this equation. Now let us use this formula, minus b plus or minus square root of b square minus 4ac by 2a formula. Now this is nothing but minus 1 plus or minus root 3 into I by 2. This is nothing but we get minus 1 by 2 plus or minus root 3 by 2 into I. Now clearly it is of the form alpha plus or minus I beta. What is alpha in this case? Here alpha is nothing but minus 1 by 2, beta is nothing but root 3 by 2. Now clearly the roots are complex numbers and distinct values. So let us write a solution of this differential equation as like this. Required solution of 1, I am taking this as 1, let us say, is given by y equals to, here roots are complex and distinct, alpha is minus 1 by 2, that is real part of this one, beta is nothing but root 3 by 2. So we write e power alpha x into c1 beta, that is root 3 by 2 into x plus c2 sine beta root 3 by 2 into x. This gives the solution of this differential equation where c1 and c2 are arbitrary constants. Okay, now this is the way to find solution of homogeneous linear DE with constant coefficients when roots are complex. With this, I'll close this one.